Okay, so this is what we did last time, talking about the HDH system, which is made up of three components. We have a closed air. So air is the dotted lines here is going in a closed loop. Open water, we are taking it from the sea and it's being thrown to the sea again, or from a source to the same source or another source. So it's an open water loop in a way, and it's a water heated cycle. The water heating can be achieved by several ways. Um, it can be either an electric heater, which is something that we started doing in the lab definitely because the lab is a closed environment, but you can take it out and do it with solar collectors, or you can do it with rejected heat. I mean, we have done an idea in the lab that has been even patented, and one of your colleagues has finished his PhD on that unit, which is a connection of an HDH unit with a vapor compression cycle. So we do a couple of things: cooling, in addition to taking the energy rejected by the compressor or the condenser of a vapor compression cycle as the source of heat to run a water desalination system, so that we protected the environment from having high energy dump to the surroundings in form of heat. And we have made use of that heat to run a water desalination unit. Or we did before while the master student that was working with Dr. Atiya and myself, who was working with membrane distillation. And we put the membrane distillation to be, it needs also low grade heat. So we put it actually in our internal combustion engine into an exhaust of an engine there. So the engine exhaust is hot. We used this heat for heating the water, and we connected a membrane distillation unit on it. And then it becomes like driving as well as getting some water being generated. I know that Ford company did something, but it was not a membrane distillation system. It was something which is mechanically operated like the RO or so, as far as I remember. This is the balance equation for the humidifier. We start with the mass balance, and the mass balance here has mass of the water, which is coming in. That's basically this. And what we have leaving is mass of the brine, which is the rejected brine. And then there is some vapor, which is the difference between this inlet mass and the mass which is rejected. That's the vapor that will be carried by the air. Vapor carried by the air is given as m dot of dry air into the difference in the humidity ratio. Energy balance, we are basically looking at the energies in and the energies out. The energies in, there is energy associated with mass of the water. So mass of the water times its enthalpy, it is this expression. We have mass of the air times its enthalpy, which is basically this expression. Both of them have the same sign if you bring it to one side of the equation. And the energy out basically is going to be the rejected brine right here, and then air which is leaving the unit. So these are basically the mass in and the mass out of the system. And then we have a second law expression which is written here. And normally the second law expression can be written as the entropy generation is going to be in balance with sigma m dot exit is exit minus sigma m dot inlet is inlet. And sigma, because we have two components in and two components out. If you go to the dehumidifier, we have two components in and three components out. That's why we have the sigma or the summation here. Definitely we assume that the units are not exchanging heat with the surroundings, so the issue of dq over t is equal to 0 because there's no heat transfer to the surrounding. And that makes the third equation or the entropy equation, second law equation here. And we have just learned that later. Entropy is important because the less entropy generated, the better the system operation. What we see here basically is the dehumidifier. Again, mass balance of the dehumidifier. We are not considering the mass of the water because the mass of the water is coming inside closed tubes, which means that whatever mass is in, it will be out. So it's not worth considering the equation. But what needs to be considered is that the mass of pure water leaving is equal to the mass of dry air into the difference of humidity ratio between the inlet and exit streams of air to the unit, which is here. Air is hot and humid here. Here it is cold with phi equal to 1 for both cases. The energy balance for the humidifier has been given here. The mass is N. Again, we have m dot water into H water 0. This is mass flow rate N. M dot air, H air N. This is mass flow rate N. And then there is water leaving, there is fresh water leaving, and there is air leaving the unit. So these are the masses in and masses out of the system. And finally, the entropy generation expression, again, sigma m dot exit S exit minus sigma m dot inlet S inlet is equal to the entropy generation. The exit is going to be basically the heated water, the cooled air, and the fresh water. These are the exits, whereas the inlet is going to be hot and humid air and cold water coming in. The heater, basically, it is, if it's a water heater, it will be m dot water H water 2 minus H water 1, and this is the entropy generation case. Before moving forward, I would just put it in here. What if it's a modified air heated cycle? A modified air heated cycle basically is going to be made up of, maybe it's worth considering it separately, because it has just a little or a simple trick related to the water, to the air heated cycle. Let me assume that I have an air heated cycle here, where we have basically the two components. One of them is the humidifier, the second is the dehumidifier, and we have an air heater here. Then definitely we have, let's assume it's a closed air cycle, so air comes in here, air comes in here, air comes in here to make a closed cycle of air, and then the water would basically be like cold water in, and then water is going to be sprayed here, and then the brine is going to be rejected. So when you are talking about the water, you will have water in, it will be sprayed, and then m dot brine is going to be rejected. So that is basically air, and this is Qn. And Qn here, I said last time or yesterday that I cannot write it as m dot air, Cp air, T air out minus T air in. This is going to be incorrect, because it's not dry air which is coming in and out. Let me assume that this is state number 1, this is state number 2 for the air, this is state number 3. So it should be Qn is m dot air into H air at 3 minus H air at 2, assuming that air is moving in this direction. So the enthalpy, why the enthalpy? Because the enthalpy is a function of temperature and omega, or phi, temperature and humidity. So you are considering the humid air condition here. The trick I would like to mention here, when you are talking about the energy balance and mass balance, there's no problem. They are basically the same. Here we should have some sort of m dot pure water as well. So the same conditions of air coming in with its enthalpy, water leaving with enthalpy, water is coming in and leaving as it has generated or it has recovered some of the energy of the hot air. This all are here. Actually, here air is coming at the maximum temperature, and it should substantially heat the water, and then the water is going to act in heating the air as it is moving up in the humidifier. When you come to the analysis, there's something that you should be aware of. We assume phi here is equal to 1. Saturated condition. We assume phi here is equal to 1. Saturated air leaving the humidifier. But for state number 3, phi is not equal to 1. Actually, it's much less than 1. And what we notice in, just to link between the different components or different states of the unit, that omega 2 and omega 3, these the ones that are equal. To linking state number 2 to state number 3 is done through the same humidity ratio. Why the same humidity ratio? Because inside the heater there is sensible heating only. There's no evaporation and there's no condensation. And that's why the water vapor content in the air remains the same. Temperature changes. Because of the increase of the temperature, the value of phi here is going to be less. But the value of omega, which is how much kilograms of vapor per kilogram of air, this is going to remain constant. And this is the key for analyzing cases or solving problems that are dealing with modified air heated cycle. So keep this in mind, because sometimes you might be facing a case or a problem where the trick is just to know that whenever you have sensible heating, definitely, or sensible cooling, then there's no condensation or evaporation, and then the omega, the humidity ratio or absolute humidity, remains constant or unchanged. So that's what I wanted to put in front of you here, and the same idea in terms of defining the effectiveness of this unit, the humidifier and the dehumidifier, remains unchanged. It's the same. Now, any questions? Okay, if not, then what we need to do today is a couple of things to consider. One of them, I'm going to share with you some results of some work that we have done earlier. Actually, it was a university project, and through that university project, we have built the unit in the lab, and we tried to come up with an idea. We wanted to see, what if we need to design an HDH unit? Normally, in reality, what the problem can be like this. We need a desalination unit for a certain community that can provide us with a certain amount of water. Let me put it that way. Now we're talking about a design example. In that design example, we need to come up with a system. The system is going to produce 10 liters or 10 kilograms of water per hour. So over the whole day, for 24 hours, we expect something like almost a quarter of a cubic meter. These are the needs. This is basically what we need to get. Do we need some specific information more? Yeah, we can assume some. We can, for example, say that we are going to rely on low grid energy, so that I'm going to have like a rejected energy or rejected heat, which is not going to exceed a temperature of 60 degrees centigrade. This is the maximum temperature of the cycle. And the cold water that we have is coming at a temperature of 30 degrees centigrade. Then build a system. You're going to make your assumptions. The assumptions are going to be, for example, what is the effectiveness of the dehumidifier? Say, let's assume we have 85% effectiveness of the dehumidifier, and effectiveness on the humidifier is also in the order of 85%. What we did then, we did some sort of detailed analysis, like the ES program that you have seen last time. We have considered that, but we tried to look for some sort of maximization of the productivity and trying to minimize the energy input as much as we can, which means that basically we're looking for maximization of the GOR, the gain output ratio. We did the analysis, mass balance and energy balance, and second law analysis for the humidifier, for the dehumidifier, as well as for the heater. We put that into the engineering equation solver, trying to come up with some values with a target of having the unit productivity is being specified. Even taking it one step further and coming up to determine what would be the right size. I'm talking about a design. So design means sizing. What is going to be the height of the packing material in the humidifier? What should be the dimensions of the dehumidifier? For example, what should be this width? What should be the depth of the humidifier normal to the page? If it's going to be a parallel pipe shape, you might do it cylindrical, it's all up to you. And then how much would be the total surface area in the dehumidifier, which is good enough for condensation to be complete? So these are the kind of questions that we wanted to do. And we wanted to make it easy for engineers who need to do a system so that they don't have to go through the detailed design. So we prepared a paper, which is basically a paper that appeared in Desalination Journal in 2014. That was about 5 years ago. And there's some knowledge that we knew earlier. Part of it is if you are going to make a system and put the mass flow rate ratio in the x-axis and change it to see what is going to be the GOR, the mass flow rate ratio MR is nothing but M dot of the seawater divided by M dot of the air. We found out that this is one of the major parameters that we consider that would affect the operation of the system. How the effect would be? There is an optimum value here. And that's something that we have tried and see, and there are even several papers from our group, whether we have done it here alone in KFPM or earlier when we were doing the analysis along with the colleagues in MIT. We found that for water heated cycle, for modified air heated cycle, there is an onset, there is a point where the GOR is maximized at a certain value of the mass flow rate ratio. So there's an increase of the GOR as you increase the mass flow rate ratio up to a certain point, and then there's a decrease. When you try to make sense of that, why this is happening, you might imagine it as if you want to increase the mass flow rate ratio, then you either increase the mass flow rate of the water or decrease the mass flow rate of the air. Now you can imagine that we have a humidifier, and in that humidifier, there is water that is being sprayed. And air is coming. Let's assume that the flow rate of the air is constant. And you have a certain amount of water flow rate which is being sprayed. What is going to happen is that the more water you add, the more vapor is going to be formed, which means that the more air is going to carry the outlet of the humidifier up to a certain point where air is basically saturated. So air is saturated at a given temperature, and you cannot make it carry more water vapor. Additional water that you are going to spray is going to make a problem for you, because we said that the GOR is M dot distillate into HFG divided by QN. HFG is roughly constant. I mean, it's a weak function of temperature, it does not change a lot, which means that the GOR can be affected by how much is the distillate, the product that you are producing, and how much QN, how much energy you are adding to the system. Let's get back to the thought example that I was talking about a while ago. If we have constant flow rate of the air and you are increasing the water more and more, as long as air is able to carry water vapor, it's fine. It means that M dot is going to increase. So the GOR increases. But not only the goal increases, you are talking about increasing the flow rate of the water, which means that Qn, which is going to be m dot water, Cp, T maximum, minus Tn to the heat. And you're increasing the water, then you are increasing m dot, you are increasing Q. But at a certain condition, as long as the air is able to take more moisture, the rate of increase of the product is higher than this, so the gore is increasing. Until you reach for a point here where the system cannot take any more. You reach the maximum. And the air has become totally saturated here at the given temperature. Then adding more water, it means you are increasing the flow rate of the water. You are increasing this, but air is not able to take any more vapor. So m dot is constant. So what will happen to the gore? It will start decreasing. And that's what's happening here. So you can look at it from this angle, or you can look at it from the other angle, that you have a certain water flow rate and you are introducing air, you are increasing air, decreasing the air. Anyway, the idea remains the same. If you are fixing the water flow rate and you are admitting the air in, you are going to have small amount of air, which means that it is not, it's not making full capacity. It's not carrying all the water vapor it should. Increasing the air can carry water vapor more and more until dilution becomes, so that you are adding air that to cool down the water while the condensation is not going to be affected. So the gore is going to reduce again. So in that sense, we see that there is an optimum value. And if you are doing a certain analysis, you better look for the optimum value of m dot r, the mass flow rate ratio, so that you can guarantee the best performance. These are the kind of assumptions that we have taken. Effectiveness of the humidifier, and dehumidifier is taken as 0.85. Temperature of the water to the humidifier is 30. Temperature of leaving the heater is 60. And then the relative humidity, which is leaving the humidifier or dehumidifier, we said earlier that it's equal to 1. As a matter of fact, you can say that it's somewhere between 90 to 10 to 100%. So you can take it anywhere between 90 or 0.9 and 1. So this is the example. What we did in that work is that we have tried to come up with figures that engineers can make use of without having to go to detailed calculations, and then they come up with a system and the size of the system. So what we're looking for here, or what's the input data for our example, is this: a product of 10 liters per hour. And the very first thing that we need to do here is that this one is going to be given as how much kilogram per second. So this is the productivity. This is m dot distillate. Feed seawater, which is entering the dehumidifier, has a temperature of 30 degrees, which is the minimum cycle temperature. And the salinity is 35 grams per kilogram, or we can say that it is 35,000 parts per million. So this is a volumetric measure. And this is basically a mass measure for the salinity of the seawater which is being used. We are supposed to be heating the water. After the heater, before it enters the humidifier, it should have a temperature of 60 degrees centigrade, and we're assuming effectiveness of the humidifier and the dehumidifier as equal to be 0.85 or 85%. The steps that we are going to do is going to be this. What we need to calculate, or the sequence of calculations, basically, it would start by calculating how much is the mass flow rate of water, mass flow rate of the air, and then what's the value of Qn, and then dimensions of the humidifier and total surface area needed in the dehumidifier or the condenser. In order to do that, we have prepared this kind of expressions that you can see here. These are figures, and the figures are basically designed for a condition of a minimum temperature of 30, maximum temperature of 60. If any one of these values have changed, then this figure is not used. And you should go for another figure for the other temperature. We did that work in 2014. And the first time I taught this course after that in 2015, I assigned a senior exam, assigned the term project for the course that would answer this question. What if the temperatures are different than 30 and 60? So it ended up with a paper that has been presented in the ASME conference, which is considering different scenarios of having maximum and minimum temperatures. What we have in these figures, you have the dehumidifier effectiveness, epsilon dehumidifier. We have the humidifier effectiveness values. These are 4 figures or 4 lines. Each one of them represents a value of the humidifier effectiveness. And in the y-axis, we have the GOR, the gain output ratio. So that in our case, what do we have? We have temperature, we have effectiveness of the humidifier, I was trying actually to come up with, so 0.85, it is somewhere here. And we construct a vertical line actually that goes up here. Assume it's a vertical one. And the intersection between this vertical line and the line of 0.85, so this is 85, 0.85 of the dehumidifier effectiveness, 0.85 humidifier effectiveness, and then making a vertical line is going to get us what is the expected GOR out of the system. So this is the first figure. The second figure is going to be, for example, knowing what is the effectiveness of the dehumidifier, again 0.85, effectiveness of the humidifier, which is 0.85, and the intersection is going to provide us with the optimum mass flow rate ratio, MR optimum, which is m dot water over m dot air optimum value. And then the last one, or the third figure, is going to provide us, again, based on what is the value of the dehumidifier effectiveness, humidifier effectiveness, and it will give us what we call the recovery ratio. What's the recovery ratio? It's how much of the seawater have we recovered as potable or pure water. So the value here is the 3. The 3 here, basically, it's 0.03. It's a percentage. So the pure water value is known because we said in the problem that we need 10 over 3600 kilogram per second of fresh water. And this ratio over MW is equal to 0.03. So from this expression, we get the value of m dot water. And then from the optimum value here, we get the value of m dot air, because we are going to have, for example, the optimum value is 2.1. So m dot water from this air is equal to 2.1. And we got m dot water from here, so we can get m dot air from here. Then I have m dot water, I have m dot air, and I have the GOR. And we know the GOR by definition is m dot pure water or product, or m dot D into HFG of the vapor divided by Qn. HFG is a constant value. Say it's 2,300, for example. M dot pure water is the quantity that we have as a condition at the beginning of the problem, which is the 10 over 3600 m dot delta D, or m dot pure water. Then this value is known. This value is known. The GOR is known from here. From this definition, we can estimate how much is the energy needed to achieve that. So the Qn in terms of kilowatt can be calculated here. And then you can realize this Qn, whether you do it with an electric heater or any other type of heater, it doesn't matter. But anyway, this is the Q which is needed for this case. So using these values, these three figures here, we got a GOR of 1.93, an optimum mass flow rate ratio of about 2, and a recovery ratio of 3.06, along with HFG is 2.345 kilojoule per kilogram Kelvin. So we made this use of this value. We could get the value of Q, 3.34 kilowatts. We get the feed seawater supply, m dot water, and we got m dot air. Now, we've come up with the physical values, physical parameters that are needed to run the program. But there's an important issue here. What about the sizing? We're going to start with the sizing here by considering some work which is related to the cooling towers. In the cooling towers, there is the definition. If the mass is being coming here, being sprayed here, then the mass flow rate divided by the area is called the mass flux. And the recommended value of the mass flux in cooling towers is somewhere between 1.5 to 4. So we're going to make use of that and say, we're going to select a value, say 1.5. So the mass flux that we are going to consider will be 1.5. What's the mass flux? Again, it is the mass flow rate of the water divided by the surface area. We selected the mass flux to be 1.5, which is this. Kilogram per second per meter square. Then we can come up with what is the cross-sectional area then, because the value is 1.5, the m dot water is something that we know. Accordingly, we're going to divide the m dot water that we have by the area, and then you are going to come up with, by the mass flux, and then you are going to come up with the area. So this is the cross-sectional area of the humidifier. It's all up to you now. You can make this cross-sectional area as L square if you need it to be a square shape, or you can make it equal to pi over 4d square if you need it to be circular shape. It's all up to you. You can design the humidifier the way that you like. If you can find a pipe of the diameter that you want, yeah, why not? That would be great. Otherwise, what we used to do, we used to get sheets of acrylic or plexiglass, cut the sheet and make a box, and the box becomes our humidifier or dehumidifier. And then we're going to make use of this figure based on the optimum mass flow rate ratio, which is about 2 in our case. And here we have a couple of lines. There is groups of lines. There is straight line and there is a dotted line. The straight line is for the case if the maximum temperature of the cycle is 50. The dotted line if the maximum temperature is 60. Our maximum temperature is 70 for our case. So it's somewhere in between. Sorry, it's 60 in our case. So it's somewhere between the 50 and the 70. And we have 4 lines here. Each one of them is representing a group of a value for the effectiveness. Humidifier effectiveness 0.65 is going to be these 2 figures, one for T water in of 50, one is for T water in at 70. And then we have this 2 lines. We have these 2 lines, and finally we have these 2 lines, the dotted ones. Now for our case, we have effectiveness of 0.85, so it's that triangle here. And we're talking about maximum temperature of 60, so it's by interpolation visually, it is somewhere in between, in the middle between these 2 lines. So for this value of the mass flow rate ratio, optimum value, and it will hit the required value that represents the heating mode, and then you can go to the left here and you can calculate what should be the height of the packing material. When we did that, we got the height of the packing material, which is 0.97. So it's almost 1 meter. So the height of the packing material is 1 meter. We used to use the cellulose, which is used for the desert cooler, and it has a height, it comes as element. Each element is having 15 centimeters high, so we use 6 elements on top of each other to come up with the required height of the packing material. What I'm talking about here, I'm talking about the packing material. I'm not talking about the height of the humidifier. I'm only talking about this L. What about the height of the humidifier from here to here? There's no formula that will help you to do that, but you just do it by common sense. I have some sort of sprayers here, so I need to have the sprayer being spreaded enough so that it would totally cover the, the top of the packing material. So we don't have dry zones, we don't have areas where no water is flowing. So this has got to be consistently done here. So you need to make the height here or this distance in a way that is going to allow for the spreading of the sprayers here in a way that's going to cover this all. And at the bottom, you need an opening for the air and you need a storage for the brine. So just leave something like maybe 1/2 meter at the bottom would be good enough to that. So that it's a storage as well as you have a way to admit your water in. I mean, you have enough area for the water to come through. So the packing height is obtained from the figure, but the rest, the height of the humidifier itself, is something that depends on the condition that you have in the problem, that you have while you are building the system. I'm sorry. So that was basically all what you need about the design for the humidifier. Then for the dehumidifier, we're going to get back again to the heat transfer course and say that we need to, now it's a design of a heat exchanger basically. So what you need is C minimum, which is m dot Cp for one of the fluids. You have to calculate m dot Cp for the air, m dot Cp for the water, and you are going to get the value which is less. Heat capacity ratio of the air is 0.053, whereas the value for the water is 0.63. So that is basically our C minimum. The ratio between them, which is C minimum over C maximum, have been calculated to be 0.146. And you can do that here, the capacity ratio and the effectiveness, and you can come up with the number of transfer units. What's the number of transfer units? It is the overall heat transfer coefficient into the surface area divided by C minimum. Overall heat transfer coefficient, you can get back to the correlations that can be used for condensers, and you can come up with an overall heat transfer coefficient value. C minimum is m dot Cp for the air. The number of transfer units can be determined from here, and the only unknown here becomes the surface area. So you do that to calculate what should be the surface area. If you are going to have tubes, so knowing the diameter of the tube and the length of the tubes can determine how much would be the length of the coil that is needed here. So the surface area that you calculated from this formula is going to equal pi dl. If you have large number of tubes, it will be n into pi dl. L is the length of the tube and n is the number of tubes. And this is typically what we do, because normally for condenser we prefer to use like the fin cooled units. You have a header here, another header here, and there is a lot of pipes in between, like the radiator of the car. And there is fin systems here, or fin surface, so that you can increase the heat transfer coefficient or the heat transfer rate as much as you can. Or alternatively, you can use a figure like this. If you know what is the overall heat transfer coefficient of the system that you have, and it is a water heated system, then from here you can get the surface area right away. So that's an alternative way, knowing what is the overall heat transfer coefficient and knowing what is the mode of heating that you have, then you can come up with right away a value of the surface area. Now, this is it. These are the steps that you would do for the design of a system, and we designed our unit in the lab based on that. The unit really it's providing us with 10 kilograms per second of water for the air, for the water heated case, but the goal is a little bit higher, which means that in the design of the unit that we made in the lab, there was something there that was, it affected the goal. Everything was fine, but instead of having a goal of 1.9, we got a goal of 1.2 or so, I mean, in that order. That would bring us back to another issue. We have in that paper, we have similar figures for the air heated cycle, and then you can follow a similar procedure to design a modified air heated cycle to provide us with 10 liters per hour. And at the end, we came up with a comparison between both of them. For the water heated cycle, the height of the humidifier was big. The packing material height was 1 meter almost. Whereas the area needed for the dehumidifier is not substantially high. It was something like what's the value? Can we get it from here? Yes, 11 meters square. This is not huge. So we're talking about a humidifier where the packing material inside is 1 meter. Maybe 1 meter 75 or like a quarter to 2 meters would be enough for the whole unit, or maximum 2 meters for the whole unit. Whereas for the dehumidifier, we're talking about an area which is 11.7. When we did the same analysis to produce the same quantity of distilled water for a modified air heated cycle, we found the height of the humidifier is small. It's something which is almost 1/3 of this. But the size of the dehumidifier was quite substantially high compared to that. And this here, something has to do with the nature of heating that you have in your cycle. Is it water heated or air heated? And the difference there becomes significant. So I'm going to post this paper on the Blackboard. Please have a look at it and just see it. And probably you can go for the examples that we have done. It's the same example to produce 10 kilograms or 10 liters per hour. And we are realizing that by a water heated cycle or an air heated cycle. The question would be, for the same unit that we decided, the plan was to bring a unit that can get us with 10 kilograms per second. Our initial calculation showed that we have a gain output ratio or a GOR equal to 1 point something. So I think we got that here in the first thing here. We're talking about a GOR of 1.93, almost. But in reality, when we did that in the lab, we got a lower GOR. I have to address this issue, and I have to bring another point to to your attention, which is something I mentioned last time when we were talking about the system of the definition of the effectiveness. Last time we talked about it, and we have written the definition of the effectiveness, and we related the definition of the effectiveness to the terminal points. And we said we have effectiveness for the water, effectiveness for the air, water side, air side, and we take the highest one of them for the humidifier, and then for the dehumidifier. The interesting thing is that we were always not convinced. If I'm talking about a humidifier, which is a system for humidifying the air, why should I be looking for the maximum value of, or should I be looking for the effectiveness on the water side? If my target is to humidify or dehumidify the system. But according to the definition, you'll find that yourself in the middle of a problem, the effectiveness of the humidifier was higher, and then it has changed in the problem, and it's changed in the middle of the problem. You can find that the temperature effectiveness of the water side has increased, so you switch directly from here to there. That was something that we were not very much comfortable with, I mean, from the physics point of view. But that was the only kind of definition that we had, and we have to live with this. Until recently, we revisited this issue. But anyway, before I start to do that, I would, just to complete the picture or the story, this is one system where we had a student, Sameh al-Mu'tasim, and Sameh did an analysis on Hth cycle, in which what we're thinking of is we are having a dehumidifier where the cold water come in, and the cold water receives energy from the condensing water vapor here, and then the water leaves at a certain temperature here. Suppose that it's entering at 30 degrees centigrade, and then we found that it might be leaving at something like 39 degrees centigrade. I'm talking about the experimental setup that we had in the lab. And here we are heating the water to about 70 degrees centigrade. It is sprayed, and it is leaving at a temperature of 47 degrees centigrade. According to the setup that we talked about earlier, there is energy recovery here, and you take this recovered energy and then you heat it further to about temperature of 70, and then you spray it there. And then we said, why should we be doing that? Why don't we take this water, which is hotter, and reroute it back again and make this water only as a backup? And according, I mean, when you look at it, it would make much sense, because why should I heat the water from 39 to 70, whereas I can heat it from 47 to 70? The recovery ratio of Hdh systems in the order of like 3 to 4% to 5%. It's not significant. So the concentration of the water which is leaving, or the brine which is leaving the humidifier, is not significantly higher, which means that you can reroute the water and you don't have to worry about the increase of the salinity. This is recirculation of the brine. All you have to do is to make up the quantity of water that has evaporated by bringing this preheated water, and you put it in, I mean, to the system. Maybe you can put it here as in this mixture as some sort of recovery for the quantity that has evaporated. And then the question, which is the system that is going to provide us with an inlet temperature of 70 and outlet temperature of 47? Is it related to the effectiveness? The answer is yes. If the system has higher effectiveness, it means I'm going to effectively cool down the water from 70 maybe to 35. In such a case, it does not make sense to use this water, but I should use this one because it's hotter. So generally speaking, the idea of brine recirculation in the Hdh system is actually associated with a condition of lower effectiveness. If the effectiveness is low, then this temperature is going to be higher, so I better recirculate it. But if the system has high effectiveness, then the temperature of the water leaving is going to be quite low, to the extent that this one is higher than it, and then I would make the energy recovery in the dehumidifier as the source of water to the system. So that's a condition that you should keep in mind. These are some of the results that we got for this system. I'm not going to discuss these results now, but I can put the paper for you here on the system. And you can see here there are conditions where the system is operating with the idea of recirculation. It is associated with the effectiveness of 0.3, 0.5, 0.47. This is where you can get, I mean, especially for the humidifier, 0.43 and 0.45. This is 0.47. This is the effectiveness that is going to result on high temperature leaving the humidifier. And then you better use it instead of the flow coming from the dehumidifier. In case of high effectiveness, you would not do that at all, because high effectiveness, it means that the water which is going to leave the unit is going to leave it at, or to leave the humidifier at low temperature, so that it's not worth rerouting it again. The temperature of the water leaving the humidifier will be higher, and you should take it. And you can see here that the GOR increases substantially with the value of the effectiveness. Here we are talking about a GOR which is less than 1, 0.6, 0.7. But here for higher effectiveness, we're talking about a GOR of 1.6. And that's another thing that you should notice for the HDH system. Look again at the example that we have given. You'll find that the value of the GOR with, if you remember, we had the effectiveness of the dehumidifier here, and the values were like this. And this is effectiveness of the humidifier. So this effectiveness is 0.5, 0.6, 0.7, 0.8, like that, roughly. Then the higher the effectiveness, the higher the value of the GOR for the dehumidifier. For the humidifier, the same thing. If you are going to move from the humidifier from 0.6, 7, 8, 9, so that's basically what you are going to get. You are going to have higher GOR with higher effectiveness. What about the dehumidifier effectiveness for a certain humidifier effectiveness? For a 0.8, increasing the dehumidifier effectiveness, it can even sometimes result in exponential increase. So the effectiveness of the unit is basically a very important parameter to improve the performance. Can you run a system with fixed effectiveness? The answer is no, because the effectiveness is a function of the flow rates and the enthalpies in and out. As the enthalpies are changing due to a change of flow rate or temperature, the effectiveness is going to change. So talking about, practically speaking, running a system on an effectiveness of 0.85, you cannot do that unless you are fixing flow rates and temperatures. But if the temperature changes or the flow rate changes, you are moving from what we call the on-design case to the off-design case, where effectiveness cannot be held constant here because it's a function of these. Al-Munzir Isam has made experiments. His master thesis was experiment on a cross-flow unit which is located on a truck. And then we had Abdurrahman Abrub in our lab, who came up with a unit which is having a cross-flow dehumidifier. So instead of having a counter flow arrangement, it's a cross-flow arrangement, as you can see here. And we did the issue of balancing here. We had a paper here which is talking about the effect of balancing that shows like a 25% improvement in the system performance. These are some of the results that we have got from this unit. And again, it's talking about the effect of, these are temperatures. But if we have extraction and injection, the red lines are showing the balancing condition versus the non-balanced condition. And definitely balancing have increased the gain output ratio for such a system. Then we made another paper with Osman Siddiqui. Dr. Osman Siddiqui is working now in the DAD, development center for the faculty, and he's working over there. He's not too far from the science, but anyway, when he was taking this course with us, he came up with a term project out of which we got this this paper. And what he was looking for is for a variable pressure system. However, some problem that we have with this system is that we use the throttle valve here. And last time, if you remember, I mentioned that the throttle valve is the worst thing to consider from the entropy generation point of view, because the entropy generation with throttling process is high. These are some of the results of the work that he has produced, and it is showing some sort of a GOR that can, for different values of the pressure, it can reach for a value of 8.4 or so. The maximum in the market is 4.5, but I have to tell you that in the market, the 4.5 is a practical one. It's a unit which is running. But the 8.5 here is some sort of theoretical work which is there, which means that when you put it on, when we try to build this system, then we don't know what kind of circumstances that will face us experimentally, and it will be a challenge to keep this kind of operation that would reach that high value of the goal. Then this is the work that has been done by Dr. Tahir Lawal, who have patented this work. And it's talking about a combination of an HDH system and a vapor compression cycle. So we have an evaporator of the vapor compression cycle that cools the seawater in to low value. The low value or the low temperature seawater will enter into the dehumidifier for effective condensation of the humid air because this temperature is low, quite low. And then after it leaves the dehumidifier, it received heat from the humidifier here. This is a modified air heated cycle because we are making use of the condenser of the air conditioning system for heating the air before it is being admitted here. So this is a modified air heated cycle. This is a water heated cycle. So the condenser has been replaced, instead of a refrigerant to air condenser, we made it a refrigerant to seawater condenser. It's a shell and tube condenser, as you can see it here, or maybe a plate condenser in which the water which is leaving the dehumidifier is heating to the top temperature, which is about 60 degrees or so, before it is being sprayed here in the humidifier. And we have different layouts. So the red one is the vapor compression cycle, evaporator, expansion valve, condenser, compressor. Whereas the HDH system is a humidifier, dehumidifier, and the heater is basically the condenser of the air conditioning system. We have like 7 or 8 papers on this topic. 3 of them are experimental ones, and the rest are basically modeling and theoretical analysis for this system. And you can see here, theoretically speaking, you can reach for a GOR which is 9 or so. So this is substantially high GOR, but the system that we designed was designed for different conditions compared to these, which means that we did not, our experiments simulate this specific kind of reading in the system. And this is showing the effect of changing the effectiveness of the unit. This is the lowest effectiveness, 0.6, and this is the highest effectiveness. And you can see here a substantial increase in the system GOR. Let's fix this to a value of 0.85 and see how much would be the increase in the GOR for a certain humidifier effectiveness. We are going from a value of almost 4 to a value of almost 8. So it can double by just increasing the effectiveness of the humidifier. The same thing applies for the dehumidifier. Say for the dehumidifier effectiveness of 0.6, we have a GOR of almost 3. But for an effectiveness which is closer to 1, say about 0.98, we're talking about an effectiveness of about greater than 4, greater than 8. So increasing the effectiveness has a significant effect on the increase in the GOR. And this probably is why we came up to the idea that the packed bed effectiveness is going to have some sort of a limit, and we better move into the bubble column units in which there's a direct contact between air and the water in the form of bubbles rising in a water stream, and that has a higher order of magnitude heat and mass transfer coefficient, and then the performance, the effectiveness of the unit is too high. The ones that we have done in the lab with a packed material has an effectiveness of about 0.6 for the humidifier, whereas the latest humidifier that we have built, it was a 3-stage bubble column humidifier, and we could reach for a value of the effectiveness of 0.92. So more than 90% effectiveness, while for the packed bed humidifier, it was about 0.7 or so. So a substantial increase due to the due to this change. And that would realize what I mentioned when we were moving from the solar cell to the HDH unit. I said that you can separately design each component of these. Yeah, it's 6:30. So I'll stop here, and next time we are going to continue with the HDH also. But I'm going to raise an interesting point, just to show you some flavor of it before you leave. When you are talking about the effectiveness of the humidifier, of the dehumidifier, we said that basically we are, and the humidifier also, we are basically relying on the terminal points. By terminal points, I mean at the exit of the humidifier, we're looking at the values to see, well, we're looking at effectiveness of, say I'm talking about the dehumidifier, hot air coming in, and then air leaving there, and then we have, cold water coming in, and then preheated water leaving here. So basically, the kind of pinch of temperatures is related to the terminals here. We're looking at water which is being increased in temperature in a linear manner, and the air is increasing in temperature in a form like this. So when you are looking at any location, if this is the enthalpy and this is the temperature, at the difference of temperatures, it becomes less only at the terminal. If you are going to extend this, then you are going to have a difference, which is this. And here you are going, if you extend this, you have a difference, which is this. So the pinch temperature is minimum at the terminals. Accordingly, the definition of the effectiveness for the dehumidifier is fine, because the values that we have considered here are the values where the temperature difference is smallest. Anywhere in between, the temperature difference is large. We will see that this is not the case if you are comparing this with a humidifier. In a humidifier, you have hot water coming in, and it decreases in temperature as it moves in. The terminals are the points where the temperature difference is so far. If we extend this further, I'm going to stop here to here. Then you are talking about a terminal temperature difference which is too high. So the issue of the effectiveness of the humidifier is the one that needs to be revisited based on that. This is going to be our topic next time. So I'm going to stop here. And as I mentioned, I'm going to expect your selection of the term projects. Just get to the to the Google form I made and make your selection. And then after that, we can discuss your selections next time, inshallah.